In Chapter 9, you learned how to do a hypothesis test, and the test statistic that you used was the z-test statistic. The process for doing a hypothesis test can also be done with a t-test statistic, and that's what Chapter 9 is all about. Chapter 9 and Chapter 8 are very similar, but there are some subtle differences that I'll be explaining in this presentation. So let's go to the first slide. In Chapter 8, the formula that you learned for doing a z-test or using the z-test statistic was to find z, take the sample mean, subtract from it the population mean, and divide by the population standard deviation, or sigma, over the square root of the sample size. So what you were doing then is you had a sample, and that sample had a mean. And in most cases, your sample mean will never be the same as your population parameter, because the only way that would happen is if your sample was the whole population. Then your sample mean and your population mean would be the same. But when you take a sample, let's say if a population has 1 million people and you took a sample of 1,000, your sample mean will not be the same as your population mean, but it'll be close if you took a good sample. Now, sometimes that mean, for theoretical reasons or because you did some type of an experiment with the sample or some type of an intervention, will be different from the population mean, and we want to know whether that difference is due to sampling error or whether that difference is due to the fact that you did something different with the sample. And that's what your numerator is telling you. Your numerator tells you how different your sample mean is from your population mean. How different does it have to be? That's what your denominator indicates. That's called the standard error of the mean. That's the typical difference we expect. And when you divide that typical difference into the actual difference, you get a z-value, and the size of that z-value will tell you whether that difference is statistically significant or not. When you're doing a t-test, or you're using the t-test statistic, we have a slightly different formula. To get the t-statistic, we take the sample mean, we subtract from it the population mean, and we divide by the sample standard deviation over the square root of the sample size. We get a difference a deviation score. We see that difference, and we want to know, is that difference large enough to say that the sample mean is really different from the population mean for theoretical reasons or because of some intervention, or is this difference due to sampling error? How large a difference does it have to be for us to make that judgment that it's due to a real change or it's simply due to sampling error? Sample means should look like population means unless something changed. Well, did something change? Was there something about the sample? Was there some kind of treatment? Well, what would you expect? That's why we look at our denominator. Our denominator tells us what to expect. This is the expected difference or the typical difference. It's called the standard error of the mean. You're familiar with that term from Chapter 8. And when we divide the typical difference into the difference that we got, we're going to get a t-value, and that t-value is going to have some likelihood of occurring, or some probability that we go to a table to find out. If the t-value is large, meaning if the t-value is large, this difference had to be large enough for us to say there is a real difference there. It's not due to sampling error. If your t-value, on the other hand, is small, then it's probably due to the fact that there's not that much of a difference here, and that t-value is due to sampling error. Now, however you understood the z-value, your t-value is very similar. So don't get confused by thinking, well, we're doing something very, very different when we're doing a t-test. The only thing we're doing different is where we have a sample standard deviation in our numerator, where with the z-test we had a population standard deviation. But if you understood what a z-score is, or what the z-test statistic is, then the t-statistic is just like that. It's very similar to it. If we had a very large sample size, your t-statistic and your z-statistic would almost be identical. But when you have small sample sizes, there will be some variability, some variation between what your t-value is and what your z-value is. And Chapter 9 explains why those differences occur. So with the t-test, to do a hypothesis test with t, you have a sample, you have a reasonable hypothesis about the population mean, you learned how to specify hypotheses, null and alternative hypotheses in the previous chapter. The problem will give you the sample standard deviation. The problem will not be giving you sigma. Sigma is what you use for a z-test. It's when you know the population standard deviation. The two general situations when you would do a t-test would be, one, when you want to determine if a particular intervention or a particular treatment caused a change in a population mean. If we had a population, let's say the population was of children who had dyslexia or reading problems, and their average score on a particular reading test, let's say, is 80. And we have a way of helping children who have dyslexia, so we take a sample, and that sample is going to have a mean, it's going to have a standard deviation. And our question is this, if the intervention worked, if this special way of working with children who have dyslexia, we'll call it our intervention. If the intervention were successful, then the reading score for children who've been through it, who have dyslexia, should be higher. Let's say it's 90, and our standard deviation, let's say, is 10 points. And what we want to know is this 90 different enough from 80 to say that the intervention had an effect, or not? Or is that 10-point difference simply due to sampling error? That's one type of that's an example of how you would use the t-statistic. Occasionally there will be a theory that might provide a hypothesis. Let's say, for example, that someone says that the average student at the University of Texas, after 4 years, accumulates $20,000 in debt. And so the population parameter would be $20,000. However, I think that students who come from a particular part of the country, who come to the University of Texas, have more debt. And so I select this sample and I do a survey of these students, and I find out that they have $25,000 in debt. And I want to know if that $5,000 difference in debt for students who come from a different part of the country than Texas is due to sampling error, or is there something different about that sample? That would be another reason I'm not to do a hypothesis test, a t-test. There isn't any intervention or treatment. It's just a theory that says this group might be different from the population group. The important thing, again, is to remember that whenever you take a sample from a population, your sample mean will be different from the population mean. And what we're trying to determine with the hypothesis test is, why are they different? Are they different because it's just due to sampling error? And if that concept of sampling error isn't familiar to you, go back and read about it. I think it's in chapter 7 or chapter 6 where they talk about sampling error. Or is it due to the fact that an intervention worked, or that we're dealing with a group that's slightly different from the population? And where the last bullet says the goal for hypothesis test is to evaluate the significance of the observed discrepancy, that's another way of saying we want to know whether the difference between the sample mean and the population mean is due to just simply sampling error, or is there a real or significant difference due to the fact that a treatment worked or that there's something different about the sample we selected. And the hypothesis test is the way we decide. We get a sample mean, and we have an assumed population mean, and we want to know whether they are different due to sampling error or different because of treatment in some way, and we subtract one from the other, and that's our numerator. So we calculate how much difference. To get that difference, that deviation, we take the sample mean, we subtract from it our population mean. We don't know how big is big or how different is different. To find out, we have to divide by the typical difference. And when we don't know the population standard deviation, then the typical difference that we divide by is the sample standard deviation over the square root of the sample size. And if you remember from the previous chapter, we call this the standard error of the mean. And it's an estimated standard error, or this talks about, and we use the term estimated because we don't know the standard deviation of the population. We haven't been able to get access or measure everyone in the population, so we're estimating the standard deviation of our sample. We're estimating the population standard deviation to be something similar to it. So here again, notice the symbols: sample variance, sample standard deviation. We have the letter S because we don't know the population standard deviation, which is sigma. When you do know the population standard deviation, then you can use the z-test. But when you don't know it, then you have to use t. So the formula for getting the standard error, which is our denominator of our formula is t equals sample mean minus population mean. We have the discrepancy over the sample standard deviation over the square root of the sample size. This is our estimated standard error, and it's called the standard error of the mean, and this symbol here should be a square root. The t-statistic then forms a ratio. We get an obtained difference. This is the difference you see when you subtract your sample mean from your population mean. And to judge whether that's large enough to say that there really is a difference between your sample mean and your population mean, we have to divide that by the standard error of measurement. This is how samples typically differ from the mean. And we divide how samples typically differ into the difference that we got. The t-value will be telling us how many of those typical differences are in the obtained difference. And then we have a value that we bring to a table and determine what is the probability of that. And if the probability is very unlikely, given our null hypothesis, then we might reject the null hypothesis. Or if that probability of that, if the t-value that you get is not a very improbable value, then we would not reject the null hypothesis. And that's the process that you learned about in the other chapter, in chapter 8. So if you get a large value for t, that means that this difference between the mean and the population mean is containing a number of typical differences, and that means that that difference that you see is probably because a treatment had no effect. But if, on the other hand, this difference is small, and when you divide the standard error of the mean into that difference, you get a small t, that means that that difference really isn't statistically significant and you can't reject the null hypothesis. So if you're doing an experiment and you hope that the experiment works, you want the t to be large so you can reject the null hypothesis that the experiment didn't work. A few more points about that formula. Let's focus on the denominator. As that standard deviation gets larger, that means that the denominator gets larger. If f goes from 50 to 60, and the sample size stays the same, then that denominator, the standard error of the mean, will be larger. And when you divide a larger denominator into the same difference, your t-value will get smaller. Conversely, as s gets smaller, the denominator becomes smaller. And when you divide a smaller denominator into that same obtained difference, the t-value will get larger. So the more variance, the larger your standard deviation in your sample, the smaller your t-value becomes. What happens as sample size changes? Well, if your sample size goes up, if you take another sample and make it much larger, then when you divide a larger sample size into the same size standard deviation, your denominator becomes smaller. And when you divide a smaller denominator into a same size obtained difference between a sample mean and a population mean, your t-value gets larger. Conversely, if n is getting smaller, if you have fewer subjects, you would be dividing a smaller number into a standard deviation, and your denominator would get larger. And when you divide a larger number into that obtained difference, your t-value will get smaller. So you might want to play with some figures, make up some numbers, and vary the size of s, vary the size of n, and see how as s varies, t varies. As n varies, how does t vary? But learn the relationships between size of the standard deviation and size of the sample and the size of t. As your variability gets greater, t tends to get smaller. As your sample size gets greater, t tends to get greater, because as you divide a large number into a same number, this becomes smaller. You divide a smaller number into that obtained difference, this becomes larger. So try to understand those differences. So think of the t-statistic as kind of like a z, or an estimated z. We estimate because we're using sample information to make a judgment about a population. When you have a very large sample, if you had a sample of 500, 600 people, then your t-statistic and your z-statistic would be the same. But when you have less, they vary a little. There's a slight discrepancy. If you remember back when we talked about the normal distribution and probability, we said that think of a distribution shaped like this as a probability distribution. Probabilities are areas. What's the probability of a z-score? And we talked about translating our distribution of scores into a z-scale, and what is the probability of getting a z-score between these 2 points? So what is the probability of a z-score less than a particular point? Or what is the probability of getting a z-score greater than a particular point? And the probability was what we learned from our normal curve table. Well, when you're using small sample sizes, as you can see, the shape of the distribution is slightly different. Your probabilities are slightly different. And that's why we need a different table or a different procedure for doing, when we use t-tests, a different way of computing the probabilities, or a different table that we go to, because the shapes of the distributions are not the same. And the shape of that distribution will depend on degrees of freedom. Your chapter explains a little about degrees of freedom. And think of degrees of freedom as sample size. If you had a sample where you had 20 people in it, then the degrees of freedom is equal to the sample size minus 1, or you have 19 degrees of freedom. And what 19 degrees of freedom was, that of those 20 people in your sample, every one of the scores, or every one of whatever you measured, every one of the mileage that tires got, or every one of the weights of a particular product, was free to vary, was random, could be anything except for one of them. And so, give you an example. Let's say that I told you that I have 5 numbers in mind and they add up to 20. And I say, give me one of those numbers. And you say, all right, well, I think one of those numbers is 4. You could have chosen any number from 4 to 20. They have to add up to 20. You said, well, one of those numbers is a 4. I wrote that down. Give me another number. Well, I can guess again, if any number from 0 to 20, I'll guess it's a 6. Okay? You are free to choose. That number could be anything. You are free to vary whatever. That number is free to vary in any number of ways. I would say, give me a third number of this set of 5, and you'd say, I think it's 2. I'd say, fine. Give me a fourth number, and you would say, I think the fourth number is 4 again. So now I have 4, a 6, a 2, and a 4, and these 5 numbers in this set. They all have to add up to 20. You had freedom of choice for 4, for 6, for 2, and for 4, but they have to add up to 20. So when you select your fifth number, it has to also be a 4, because the total has to be 20. These 4 numbers, you were free to vary. This was not. So when we say there you have a sample of 5 with 4 degrees of freedom, that means that every number was free to be whatever it wanted to be except the last one. If you have 20 people in a sample, you have 19 degrees of freedom. If you have 30 people in a sample, 29 degrees of freedom. So think of sample size and degrees of freedom as indicating basically the same thing. Again, we have an alpha level, just as you did in just as you understood from Chapter 8. The alpha level is how much risk are you willing to take when you say that a population mean is different, that a sample mean is different from a population mean. We talked those alpha levels can be 0.10, 0.05, 0.01, 0.001. The larger the alpha level, the greater the risk of making a type 1 error. The smaller the alpha level, the less risk there is of making a type 1 error, but the greater risk there is of making a type 2 error. So make sure you understand the trade-off between type 1 and type 2. We have a critical value again that you get from using a t-table. To get this critical value, which is the value that you need to exceed in order to reject the null hypothesis, you have to go into your table and use degrees of freedom to tell you what is the critical value for a one-tailed test or a two-tailed test for a particular alpha level of 0.05, 0.01, and your chapter explains how to use that table. If the obtained difference that you got when you got your t-value from subtracting the sample mean, the population mean from the sample mean and dividing by the standard deviation or the square root of n, your critical value tells you how large this has to be. If this difference is very large, you'll get a large t-value, and then if it has to be larger than the critical value, and if it's larger than the critical value, you would reject the null hypothesis. We went through that process in Chapter 8. Here are the steps for the hypothesis test. They're the same tests, the same steps that you went through with the z-test, only we're using the sample standard deviation to calculate the t-statistic. So we use t then if we have a hypothesis about a treatment and we think that this treatment is going to change the population average in some way for this sample. If the treatment worked, then the sample mean or the estimated population mean that we know from the sample might be 35. And we'd say, oh, the treatment boosted the score in some way, or boosted the weight in some way, or boosted the miles per gallon for the cars in some way. On the other hand, if after the treatment our mean or our sample mean is very close to the population mean and we project a population mean from our sample of 30.5, we would say this difference of 0.5 is simply due to sampling error, and we would not reject the null hypothesis. Same kind of decision making that you used in the previous chapter.